Okay, so I didn't quite get it finished before the video ran out. But if you square your 1.12 times 3, divide by 0.8 squared, you should get 5.88, and the units will end up being newtons per meter, or kilogram per second squared. Second part of the question wanted to know what is the period of the oscillation. So that's t, and remember t is equal to 2 pi root, and this is where you have to pause and think, is it m over k or k over m? Okay, and so we have our k, it's m over k by the way. We have our k, the m is 3 kilograms divided by 588 newtons per meter, and when you do this you should get a t of 4.4 something, maybe 88 I think, if I could see seconds. Alright, number 12. Next up is number 14, my pet frog, Carol. I haven't met my pet frog yet. I was going to use Harold the snail, but he doesn't hop well. So this is one of those two angle ones, okay, that you need the double angle identity for. So Carol, my pet frog, can jump 64 centimeters, or 0.64 of a meter, horizontally on a level surface. After careful study, I determined her initial velocity is 4 meters per second. When she jumps, what are the two possible angles? Okay, so remember, divided into x and y. We have a VIX, which we don't know. We have a VIY, which we don't know. VI, and the y will be sine theta, and the x will be cos theta. AX is 0. Delta dx is 0.64 of a meter. AY is 9.81 meters per second squared. It's going to be down. This is going to be up. Okay, and we use that little trick of the half time, right? So we look at just up, and we say, okay, at time up, we know AY is equal to VFY minus VIY over delta t, but if we're looking at the up, that becomes u, and this goes to 0. Rearranging for tu, then we have minus vi sine theta over ay. So delta t total would be equal to negative 2 vi sine theta over ay. And so then we go to the x direction, and I'm just going to do it up here. We know delta dx is equal to VIX delta t, 1/2 AX delta t squared, and this goes to 0. Okay, so we have delta dx is equal to VI cos theta, and instead of the delta t, I'm going to fill in this. So it'll be negative 2 VI sine theta over AY. Okay, bring my AY over, delta dx, bring my negative over, and this side will be negative, or excuse me, I took the negative over, VI squared 2 sine theta cos theta. Divide both sides by the VI squared, so you'll have AY delta dx over VI squared. And on this side, the 2 sine theta cos theta is your double angle identity. So this will be sine 2 theta. Okay, so you'll have sine 2 theta is equal to negative 9.81 meters per second squared. The delta dx was 64 centimeters, or 0.64 of a meter, and the launching speed was 4 meters per second. Remember, when you do this, you'll get 2 sine theta, and then you'll have to divide by 2 later. So if we multiply this out, 0.64, I don't know why I put a squared on this one. The squared's down below. 0.64 times 9.81. And this goes in as a negative because it was down. Divided by 16. So you get 0.3924. Take the second function sine and get 2 theta to be 23.1039 degrees. So theta divided by 2, 11.55219, etc., but I'm going to round to 2. And so then the second one is 90 minus that. So that's theta 1. So then do 90 minus that and get 78.448 for your second one. Okay? And that's all that one asked for. All right, next up, our next page, 21 and 24. I might do 21 first just because 24 is a little long, and I need a whole new page for that. So 21 tells me mass of a satellite is 2,000 kilograms, put into an orbit around a planet, and the height is 4 times 10, if only I could see, the 6th meters. The radius of the planet is 5, so the little r is 5 times 10 to the 6 meters. So the radius of orbit is going to be 9 times 10 to the 6 meters. The gravitational field strength, little g, is 12 meters per second squared. Calculate the mass of the planet, the time for the satellite to orbit once. Okay? So I am looking for, trying to cheat here so I don't have to type everything in my calculator. So mass of the planet, the easiest way to get the mass of the planet is to use little g equals capital G m over r squared and rearrange for m, because this is the mass of the central body. So it's going to be equal to r squared g over capital M. So r squared is 9 to the 6th meters squared. Little g, you were told in the question, was 12 meters per second squared. And capital G, of course, is 6.673 to the negative 11 Newton meter squared per kilogram squared. Type this into your calculator, and you should get a mass of 1.4566 times 10 to the 25, I think it is. Yeah. Okay, so then the next one wants to know the time for the satellite to orbit once. I'd probably use Newton's version of Kepler's third law for that. Gm over 4 pi squared is equal to r cubed over t squared, and rearrange for t squared. So 4 pi squared r cubed over g times the mass that you just found. So 4 pi squared, the r was 9 to the 6th cubed, 6.673 to the negative 11 Newton meter squared per kilogram squared. And the mass we just found, that's now off my screen, 1.4556 to the 25th kilograms. Okay, remember to cube your r, square your pi, and square root your t. And if you do all that, you get 5,441. 5,441.398. 398 seconds. All right. Next up, number 24. Stack my papers here. The video is going to end, but I can at least get it started. So number 24 is your favorite, electrostatics. 3 charges are located on the corners of a right triangle. So we have a right triangle, and we have 3 charges. Okay. At one end of the hypotenuse is 4 microcoulombs. At the other end is negative 6 microcoulombs. And at the right angle is positive 8 microcoulombs.